Hello everyone, my name is Gaurang Gupta and today we will be doing another machine learning project which is Boston house price prediction. In this what we have to do is we have to predict the price of house in the Boston area depending on certain parameters like criminal activities in the town, some non-retail business distribution and etc. So here is the parameter which we have to predict, which is MEDV, median value of owner occupied houses in $1,000. Means we have to multiply this MEDV value by 1,000 to get the actual price of the house. So let's start coding. First, we will import all the necessary libraries. So import NumPy as NP, import pandas as PD, import OS, import matplotlib dot pyplot pplot pyplot as plt. Then import cbon as sns from sklearn dot metrics. Import mean squared error and mean absolute error. Then from sklearn dot linear model import linear regression, cd regressor, lasso and ridge. Then from sklearn.ensemble import random forest regressor. From sklearn.svm import svr. From sklearn.tree import decision tree class regressor. Decision tree regressor. From sklearn.neighbors import kneighbor regressor, kneighbors regressor and radius neighbor regressor, radius neighbor regressor. From sklearn.gaussian process import Gaussian process regressor, Gaussian process regressor. From sklearn.gaussian process dot kernels import byte kernel and dot product. From sklearn.model selection import train test split grid search cv. So let's run it. Our code is executing properly. Now let's move on to next section, which is data loading. For this I will use a variable path which will be an empty string for now. Then for dir name comma underscore comma file names in os.walk slash kaggle slash input. Then for file name in file names path will be os.path.join dir name comma file name. Run it. Now we have the path. Now we will make a data frame pd.read csv and we will pass the path here. Then data.head. Run it and now we have our data in our code. We will also check whether this data contains some null values or not. So data.isNA dot sum. Run it, and here you can see we have no null values, which is a very good thing because then we will have to deal with it. But here we have no null values, so we don't need to code for that. So now let's move on to next section, which is data pre-processing. First we will get the columns. It will be list data dot columns. Then we will print those columns to see which columns we have. Then std will be standard scalar. New data will be equal to pd dot data frame. Std dot fit transform. We will pass here data. Then cnt will be 0 for call in columns. New data dot rename columns equal to cnt call in place will be true, and then cnt plus equal to 1. Now why we did this is because this new data variable, when it is scaled, it will lose all the column values. Every column will be renamed from 0 till the column length minus 1, because this std.fit transform, it changes the pandas data frame into a numpy array, into a multi-dimensional numpy array. So we have to convert that numpy array into this data frame, and then the new data frame should be renamed so that we can access that easily. You can skip this step if you are willing to deal with this renaming, and you can remember that yes, this number column represents this. For example, 0 represent crim and the last one represent midway, but I'm renaming it just so that it is easier to deal with. Now let's run it, and here you can see we have all the column names. Now let's move on to next step, which is data visualization. For this, first we will use new data dot describe to see description of every column. Run it, and here you can see you have values like count, mean, standard deviation, minimum, maximum for every column, and this is our scaled data. So remember, these will not be actual standard deviation or actual minimum or actual maximum of the data which was given. It is the maximum, minimum, or any of this of the scaled data. Remember this correctly, because sometimes when you change these scaled values to original values, you might use these values and this will also produce errors. So now let's move on and plot some graphs. So pig and axis will be equal to plt dot subplots 7 comma 2 comma fig size, not fig size will be 80 comma 150. You can change it. So I found this size by trial and error. It's not like I remembered this size, I just found it by trial and error. So access will be access dot label for call comma ax in zep columns comma axes plot, not plt, plot will be equal to sns dot hist plot. New data call kde will be true, then stat will be density, and ax will be ax. Then plt dot set x label, plot dot set x label, not plt, will be call comma font size will be 15. You can change it also. Let's do 35 because 15 will be very small. So pl plot dot set y label will be call, will be density, not call, and font size again will be 35. Then plt dot show. Run it. What it will do is it will plot the density for every column. wait for some time because it takes some time to complete. Now the code is executed completely, and here you can see I have the density for every variable. You can see for rm I have some Gaussian distribution, so you can say that the Gaussian might perform well, Gaussian models. Here we have tax, and then here there is some variable b, and here's our output variable medv. It is also kind of following some Gaussian process for this much range, but yes, it is deviating from it. You can draw these conclusions from these graphs. You can also use other plots, like I am using his plot. You can use any other plot, it is totally your choice. Now let's plot the heat map for this data. For this we will use plt.figure. Fig size will be 25 comma 20. Then sns.heatmap will be new data dot core anode will be true, and then plt dot show. Run it. It will take some time depending on the data. It ran quite quickly. So here you can see we have the relation of the data, or you can say relation of every column of the data with every other column. So here you can see for medv, you can see lstat, sorry, is a variable which is very negatively correlated to our medv variable, and pt ratio is also very negatively correlated with the medv. Means if lstat or pt ratio have higher values, the house will be of lower value. And here you can see the variable b, it is showing 0.33. Same conclusion, b rises, our median value of the house rises. So now let's move on and also plot a pair plot. sns dot pair plot will be new data. Run it. So our code is executed. You can see we have a pair plot for every pair present in the dataset, and the medv variable is plotted against medv, lstat, pt ratio, etc. So now let's move on to next section, which is training different models. For this, first we will have our inputs, which will be new data dot drop medv. Access will be 1. Output will be new data medv medv. Then x train, x test, y train, y test will be equal to train test split. Inputs, output, test size will be 0.2. Random state will be 0. Run it. Now we have our training and testing data. So we will define two lists, ms and ma. This will store our mean square and mean absolute errors respectively. So MSE will be mean squared error, and MAE will be mean absolute error. Absolute. Run it. Now we have our lists in place. Now let's code the function which we're going to use for model training and calculating its score. So model training and score, it will take two parameters, model and name. Then if name not equal to best model, then we have to train the model. So model dot fit x train comma y train. Then y pred will be equal to model dot predict x test. Then mean squared error will be msc y test. comma y spread. Then mean absolute will be MAE y test comma y spread. Then print name, print mean squared, print mean absolute, then ms dot append mean squared, and ma dot append mean absolute, and then we will print a new line character. Run it. Now we have function for training and score. Now we will select the models, or we will make an array of models, and then we are going to train them. So models will be random forest, random forest, then random forest regressor, and estimators will be 5, then lasso will be lasso alpha will be 0.1, then support vector it will be svr, then stochastic will be sgd regressor, then gaussian process gaussian process will be gaussian process regressor, where kernel will be dot product plus white kernel. Then random state will be 0. Random state will be 0. Then decision tree will be decision tree regressor. Then k neighbors will be k neighbors regressor. Then ridge regression will be ridge, where alpha will be 1, and then linear regression, and here we will place linear regression. Run it. Now we have all the models and their names in place. Now we are going to train each one of them. For model, in models, model training and score will be model 1 and model 0. Run it. Here you can see it will be printing the mean square and mean absolute errors of all the models. So we have random forest, lasso, support vector machine, stochastic gradient, Gaussian process, decision tree, k-neighbor, ridge, and linear regression. So if you look these values, you can see that support vector machine is the most accurate model. Now we are going to optimize our best model, which is support vector regressor. So for this, we will define a variable which is param_grid, which will be a grid containing the variable and some values on which we will try to optimize it. 1, 10, 100 and 1000. Then gamma 1, 0.1, 0.01, 0.001, 0.0001, and we are going to get one more variable, it is kernel. It will be fixed, and we will have rbf kernel, which is radial basis function. rb Not rbb, rbf. Then grid will be equal to grid search cv, grid search cv svr, then param grid prefit will be true, and verbose will be 3. Verbose will be 3. Then grid dot fit x train comma y train. Then model will be equal to grid dot best estimator. Then model training and score. Training and score. Model comma best model. Best model. Now let's run it. So here you can see it is optimizing, and the code is executed completely. Optimized it, and we have some reduction in error. Here concentrate on this mean absolute error. Here it is 0.29, and let's see what we got earlier in support vector 0.31. You can say that it is not much of an improvement, but yes, it is surely an improvement, and any improvement is better than no improvement. So now let's plot the accuracies of all the models we have trained. Before moving forward, I actually made an error. So first correct it, because the next code is dependent on that. So we have to push an array or a list here and also here. So we have to run the whole code again. So off from here and then run all. Why I am pushing name and mean absolute error both, you will get in the next code when we are going to code for this. Now for this we are going to first define a variable which is bar width, which will be 0.2. You can change it 0.2. Then we are going to define three empty lists, which will be model names, mean squared, and mean absolute. Absolute. Then for I in ms, model names dot append I0 and mean squared, not absolute, squared dot append I1. For I in MA, mean absolute dot append I1. Now fig will be equal to plt dot subplots fig size will be 16 comma 8. Then br1 will be equal to np dot a range length mean squared. You can use any array here because all three of them are of equal length. plt dot bar br1 mean squared, color will be green, width will be not width will be bar width, label will be mean squared error, mean squared error. Then br2 will be equal to x plus bar width for x in br1. Then plt dot bar br2 mean absolute color will be purple. Then width will be bar width. Then label will be mean absolute absolute error. Then plt dot x label will be models. Font size will be 15. plt dot y label loss and font size again 15. Then plt dot x text r plus bar width for r in range length mean absolute model names. Then plt dot legend and plt dot show. Run it. Now here you can see we have all the values of the losses plotted. If you look closely, you can see that random forest is showing least mean squared error, even in comparison to the best model. Let me show you here the values. Here you can see the value of this mean absolute error is less than this support vector machines mean absolute error. And when we optimized it and we got the best model, we got the optimized models mean absolute error approximately equal to, I think it is somewhat less. Yes, it is somewhat less than the random forest mean absolute error. So and now it depends on you what you want to select. If you are going to base your model error on the mean squared error basis, then surely random forest is the best. But if you are going with mean absolute error, then best model which we have optimized is the best, because the the loss here you can see is the least if we compare with all the models. But for the mean square, this random forest is best model. So this is a major point which I wanted to point out, so I repeated it. So for now our project is complete. Thank you for watching the video. If you like this video, please do like, share and subscribe to my channel. And if you have any suggestions, comments or any doubts, do comment in the comment section. I will be very happy to solve the doubts you are having. So thank you very much for watching the video. Thank you.